Hi, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video we are going to talk about the main characteristics of the Sun. As you know, the Sun is the only star in our solar system, and for all practical purposes it gives us all energy that we receive on our planet Earth. So if this is the Sun and somewhere far away is Earth, then the average distance between the Sun and the Earth is 150 million kilometers. But it varies between 149 152 million kilometers during the year. Now, Sun is enormous. The radius of the Sun is about 696,000 kilometers. Huge! That is really huge when you compare it to the radius of planet Earth, that is only about 6,371 kilometers or so. So clearly these are not to scale. Now, Sun is not only huge in terms of the size, it's also extremely massive. In fact, over 99.8% of the total mass of our solar system is only Sun. And if we break down the mass of the Sun, then we know that about 3/4 of the mass of the Sun is hydrogen. An additional 1/4 is helium. So you can see that for all practical purposes, 100% of the mass of the Sun is just these two elements. Of course, there are trace elements of anything else in the Sun, but for all practical purposes, this is the entire mass of the Sun. And on daily basis, Sun is converting hydrogen into helium through thermonuclear reactions. Now, these thermonuclear reactions can only occur in the part of the core of the Sun. And core of the Sun is the central part of the Sun where temperatures are extremely high, over 15 million kelvins. Density of matter here in the center of the Sun is over 150,000 kilograms per cubic meter. That is something our brains cannot comprehend. Now, at such high temperatures and densities, thermonuclear reaction can occur by which hydrogen is converted into helium. In fact, every second as we speak, approximately 600 million tons of hydrogen is converted into approximately 596 million tons of helium. As we speak, where is the difference in the mass going? The answer, the difference in the mass, let's call it delta M, difference in the mass, is going into energy that the Sun is emitting. And that energy, through electromagnetic radiation, goes in all directions, and part of it reaches our beautiful planet Earth and gives life on our planet. Now, in my previous two videos, I went into great lengths to explain electromagnetic radiation in general and then electromagnetic radiation of the Sun. Now, this delta M, this difference in the mass, is converted into energy, some energy delta E, through famous Einstein's equation E equal mc squared. Now, when we know these some basic properties of the Sun, and from my previous video, by the way, you know that the temperature at the surface of the Sun is approximately 6,000 kelvins, which is, as you can see, much colder than the interior of the Sun, that is over 15 million kelvins. Now, when we know these basic properties of the Sun, I would, although this is fundamental playlist, I would like to describe a little bit how hydrogen in the Sun is converted into helium. As I said, despite being fundamental playlist, this reaction is the source of the life for you, me, and everything else on this planet. So it is worth knowing it even at the fundamental level, how thermonuclear reaction converts helium into hydrogen. Let's do it after I erase this whiteboard. Since this thermonuclear reaction converts hydrogen into helium, let us look at the core of these two elements. So if we start with helium, then in the core of a helium atom, we have two protons, and these protons, as you know, are positively charged, and we will also have two neutrons that do not carry any electric charge. Now, this is a helium core, and let us just introduce some nomenclature that will help us understanding this thermonuclear reaction. In this core, we have four particles. So we introduce nomenclature where we say there is a total of 4 nucleons, and out of these 4 nucleons, 2 are protons. So in this case, you know right away there are 2 neutrons as well. Now, if we now look into the core of a hydrogen atom, then hydrogen has nothing else but 1 proton, and that's it. And therefore, we would say that hydrogen has 1 nucleon, and that 1 nucleon is proton. Consequently, if we only have a neutron particle roaming somewhere around, we would say that this neutron particle is nucleon but 0 protons. It's just 1 neutron. Okay. Now, when we know this on the right side of the whiteboard, let's first see how hydrogen is not converted into helium. If you think that hydrogen plus hydrogen can give you helium, then you are very, very wrong. This reaction cannot occur. So the sequence of thermonuclear reactions in the Sun is more complicated than this. First of all, to get hydrogen converted into helium, we have to start by converting a proton into neutron. So proton needs to be converted into neutron. And that can be done through the action of the so-called weak nuclear force, which I'm not going to explain here in great details. That might come later in the Advanced Thursday playlist. Now, when proton is converted to neutron, it also gives off a positron and some other particle known as neutrino. We don't have to worry about these particles here. Now, this neutron, I can, as you can see, write it neutron 1, 0, will react with hydrogen 1, 1. And this reaction will give us hydrogen that has, as you can see, 1 plus 1 is 2 nucleons, out of which 1 is proton. That means this is the so-called isotope of hydrogen, which is known as deuterium. Because we have 2 nucleons and only 1 proton, that means that the other nucleon is clearly a neutron. And that is and this now becomes hydrogen 2, 1. Let me use black for the consistency. Now, it is also very important to emphasize that this first reaction is very, very slow. And that is why Sun doesn't burn very fast. If this reaction by which proton is converted to neutron was very fast, Sun would burn quickly. But Sun was formed about 4.65 billion years ago, and it will last at least that amount of time because this reaction is very, very slow. Now, when we have this 2,1 hydrogen, then this hydrogen can further react with another hydrogen, and this will give us now helium. Finally, we are getting helium, but this helium will be 3,2. As you see, 2 plus 1 is 3, 1 plus 1 is 2. That means helium that has 3 nucleons, out of which 2 are protons. So we are missing 1 neutron. And that is called isotope of a helium. And this isotope cannot last long, but it can last quite often long enough to be combined with yet another 3,2 helium. And then finally, we are getting helium 4,2, this guy over here, and we also get 2 protons that stay in the core of the sun and can continue this process. Now, this helium 4,2 is stable. Now, very important, this reaction, as well as this reaction, give off energy. Energy that is released when these thermonuclear reactions are taking place is the energy that we are receiving from the sun. And this is how these 600 million tons of hydrogen are converted into helium. Again, I know this is a little bit more advanced for fundamental playlist, but I really wanted to include it because this is what gives life to all of us. I would like to conclude this part of the talk by saying this is not the only sequence of thermonuclear reactions that convert hydrogen into helium in sun, but indeed this is the most common sequence in the sun. Now, when we know this, let us move forward and investigate different layers in the sun. Now, let us look back at the geometry of the sun. As we just said, in the center we have the core. So if we zoom in the part of this core, we could say that the top of the core region is approximately 139,000 kilometers from the center of the sun. And then the energy that is created in the core of the sun radiates out, and it finds itself in the next region of the sun, known as the radiative zone. Now, in the radiative zone, these photons of energy that are produced in the core are making their way through very, very dense, still very dense part of the sun, and they usually travel in a zigzag way known as a drunken man's walk that I discussed in one of my advanced videos. So it can take them a lot of time to bounce off of many atoms that are over there and then find their way finally at the top of the radiative zone. In fact, it takes them approximately 170,000 years to pass this region. And this region, namely radiative zone, has radius of approximately 513,000 kilometers from the center of the sun. Just to give you an example, 170,000 years ago is when people started using clothes. So when you have radiation that is reaching us now, radiation that you can see outside, on average, that radiation was formed 170,000 years ago in the core of the sun, but it took it that much time to find its way to the top of the radiative zone. Now, above radiative zone, we have a small transitional region, which I will discuss soon, and then we have yet another big zone known as the convection zone. Now, this transitional region is known as tachocline, and we believe this might be the zone that is responsible, at least in large part, for the creation of very strong magnetic fields in the sun. Or at least one way or another, it might be related to the magnetic properties of our star. Now, here in convection zone, the main transfer of heat is no longer through radiation, but we actually have convection. So we have hot plasma being convected up, and then subsequently we have colder one going down. So we have these big currents of hot plasma in the sun going up and down, up and down. And now when this energy finds its way all the way to the top, to the surface of the sun, which I discussed, this is now 696,000 kilometers from the surface of the sun, this energy can go in the form of electromagnetic waves into the outer space, and part of it ends up hitting our planet Earth. Lastly, let us now discuss the layers in the atmosphere of the sun. Lastly, let us look at the atmosphere of the sun. Here is the surface of the sun. The first layer of the atmosphere is known as photosphere. And photosphere is approximately 400 kilometers thick, and the average temperature in the photosphere is around 6,000 kelvins. To be more precise, 5,778. Most of the radiation that we get on Earth comes from the photosphere. This is extremely dense region, and now you understand why I picked this number in my previous video when I did those simple energy calculations, because that's where the energy is coming from. Then the next region of the atmosphere is known as chromosphere. Thickness of the chromosphere is approximately 2,100 kilometers, and temperatures here are higher than in the photosphere. They are approximately 8,000 kelvins or so. So of course the logical question is, why didn't I pick this value as the temperature associated with the energy that we are getting from the sun in my previous video? The reason is, yes, this is hotter region than the photosphere, but the density of the material here is very low. So the amount of radiation that is being radiated out is much smaller compared to that from the photosphere, because this is much denser region of the atmosphere. And the most outer region of the atmosphere of the sun is known as corona. Like any atmosphere, it doesn't have the upper limit, but it stretches many thousand kilometers from the sun. And temperatures in the corona can be extremely high, even reaching 2 million kelvins. That is substantially higher than chromosphere and of course photosphere. We really don't completely understand why corona has such a high temperature. It is clear from research that it is related to extremely violent and strong magnetic fields that exist on the sun, but the exact mechanism is not known. However, what is known is that there is a region of only a few hundred kilometers between chromosphere and corona where temperature gradients are extreme. Temperature changes from between 8,000 kelvins in chromosphere to approximately 500,000 to 1,000,000 kelvins in corona, or even higher if the temperature in corona ends up being very high. So these are extremely steep temperature gradients. You see, this region is very hot, and that means, from my previous video, then you understand that the energy that we get from here is very energetic because it's proportional to temperature to power 4. And a lot of ultraviolet light comes from corona. Now, because again, same argument, corona is not very dense. We don't get a lot of energy from there because density of the material is low. We get most of the energy from the photosphere, but whatever we get from corona is very, very high intensity. And that is why during solar eclipse, one should not look at the sun, because you do not see sun, you do not see photosphere, but you can see corona. And the energy that is coming from corona is very high energy indeed, and that can ultraviolet, even X-rays, most X-rays are absorbed in the atmosphere, but ultraviolet light, and that can damage your eyes. Chromosphere, as you can see, is very thin region, so it can be observed during solar eclipse, but not as clearly as corona. And corona is usually those white, milky, cloud-like features that appear, and I will soon show you a few images from NASA that depict chromosphere and corona. Finally, to conclude this lecture, let us look at this figure of the sun from NASA's website. You can see many things are happening on the surface of the sun, including these big explosions. Now, these explosions are very violent and they can eject huge amount of material into the outer space, and that material that is then traveling through the space is called solar wind. I will have a separate lecture on solar wind. But for the sake of comparison, keep in mind that these explosions are many times larger than the planet Earth because the sun is so huge. If you look closer at the surface of the sun, you see it looks like it is boiling. And indeed it is. Because you will remember that the outermost region of the interior of the sun is the convection zone, as we just discussed. So these are convection cells that we see. Brighter spots are the interior of the convection cell where the material is rising, and then along the edge of each convection cell we have sinking of the material. These are darker regions with somewhat lower temperature on average. And these convection cells are pretty uniformly distributed across the surface of the sun, except for the existence of these very isolated dark spots called sunspots. You can see one bigger one here and smaller one here that is forming. They are small compared to the rest of the sun, of course, but they are very large if you compare them to planet Earth, because again, sun is so huge. Now, sunspots are dark because temperature across a sunspot is lower than the temperature across the rest of the surface of the sun. So these are colder regions on average than the rest of the sun. The formation of sunspots is still not completely understood, but we know it is linked to the fluctuations in magnetic fields that exist on the surface of the sun. So in terms of the occurrence of sunspots, we say that sun is in solar maximum when we have many sunspots across the sun, and solar minimum when we have very little to none sunspots. And here you can see this is 28 February 2014 and 18 February 2020. Now, coupled with sunspots are these faculae, which are very bright regions across the surface of the sun, characterized with higher temperatures than the average temperature of the surface of the sun. In terms of the amount of energy that we get from the sun at the top of the atmosphere of the Earth, here is the graph that shows that. So x-axis are years from 1600 to 2020, y-axis is the amount of energy that we get per square meter per second. So incoming energy in watts per square meter, but watt, as you know, is joule per second. So this is amount of energy that we get every second per square meter at the top of the Earth's atmosphere. And you can see that average is 1361 watts per square meter, but it fluctuates because activity of the sun fluctuates, and the occurrence of these sunspots that I just discussed seems to be periodic, with the period of around 11 years. And you can see these periods in this graph. Now you can also see, for example, that between approximately 1650 and 1700 we had very low solar activity, and we call that Maunder minimum, and I will discuss this much more when I start talking about climatology and astronomical effects that are affecting climate, astronomical factors, that are affecting climate on our planet. This is, by the way, the middle of the Little Ice Age, if you are familiar with that terminology, that happened between approximately 1300 and 1850. But again, you can see, if somebody is asking you how much energy do we get from sun at the top of the atmosphere, 1361 watts per square meter is a good number to give. Lastly, here we have two figures during a solar eclipse from NASA again. Let's first examine the right one. These reddish cloud-like features are the chromosphere that I said. At least the inner part of this atmosphere that we see here is the chromosphere. And then these white cloud-like features that you see here is corona. As I said, temperature in corona is extremely high, around 2 million kelvins. So the energy that is coming from corona is very high intensity energy, a lot of ultraviolet radiation, and that is why if you are now looking at corona in real life without any protection, then the radiation that is coming from here is very intense because of Stefan Boltzmann's law, because temperature here is very high and a lot of ultraviolet radiation is emitted, and that can damage your eyes. So do not look at solar eclipse without any protection. Until next video, goodbye.